I'm on three-dimensional coordinates. Here we go. We have three axes now. Positive x is one of the axes. Positive y, positive z, negative z. Now, this is called an orthogonal graph, but it's flawed. When you're trying to represent a three-dimensional, like a three-dimensional point, kind of doesn't sound right, but a point you plot using three axes. On a two-dimensional piece of paper, it's a flawed system. Okay, so this is just a representation. Here's how I would plot this point. I don't think it's a surprise to anybody that we would go in this order, x, y, z. So when I'm doing 3 on the x-axis, I'm going positive 3. 1, 2, 3. The y is 1. I run parallel with the y-axis. So a positive 1 is this way. So you can see that's parallel with the blue. If it was negative 1, I would go that way. So it's positive 1. And then the z is positive 5, so I'm running parallel with the z-axis in the positive direction, which would be up. 1, 2, 3, 4, 5. That's where A is. Okay, I will do one more. B, negative 1. So negative 1 on the x-axis is here. Positive 2, I run parallel with the y-axis. 1, 2. Positive 1, up 1. That's where B is. Okay, now more importantly, I made a little diagram here using my kids' puzzle box. This is, come on, stay. This is what we're representing. So if this is like, if I'm in the classroom, I would use the corner of the room. This would be my positive x-axis. If I went through the box that way, my negative x-axis would be, out here. My positive y-axis through the box that way would be my negative y-axis. Z, positive up. If I went through the box, going down, that would be my negative z-axis. So if I'm plotting the point, let's just say 1, or let's say 3, 4, 5. I would go 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. It's a specific location in space, like 3D space, with respect to the origin. Okay? Now, what's nice about this is that our formulas don't change. We just happen to have 3 points. So now if I consider that vector, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, it's this vector right here. I'll make it with my pen. The vector that goes from the origin out to that point. So when I'm asked for the length of that vector, I'm using the same exact formula we used before. I just happen to have a z involved. If I have a vector that goes from, I'm moving this, let's say I have a vector randomly out here, and I want to get it in standard form. I subtract, and it brings it right back here to the origin. So everything we already know is true for three-dimensional. I don't use this formula. I mean, I'm using it, but I'm not really using it. I'll explain that in a minute. If it's asking me to use example 1 up here and find the distance the point A is from the origin, okay, this distance is the same idea as the length of the vector. So if I treat it as vector A, excuse me, and I'm trying to find the length of it, I'm going 9, 1, 25 under the square root. Okay, we're treating it like it's a vector. We want to find the distance. Point C is from point D. So now this is me treating these two as though they form a vector. So I'm going to take those 2 points and I'm going to subtract them. When I subtract them, it's going to get me a standard form vector. I'm just going to write them down here. C is 2, -2, -1. D is 0, 0, 2. Okay, so when I subtract those 2 points, it doesn't really matter what order I'm subtracting them in because the direction is not important here. I'm going to get -2, +2, and 3. Now, think of this as the vector that goes from D to C. Now I have a vector, and I'm going to find the length of it. 4, 4, 9. This is the length of the line that goes from C to D, or the vector that goes from C to D. If you recall from day 1, I said we never really want to work with it from this point to this point. We don't want to work with it like that. We want to subtract them, get a vector in standard form, and then find the length of it. Boop. So CD was randomly, out here somewhere. We moved it to the origin, and then we found the R value. Okay, equation of a sphere. This should be super easy because we already know how to find the center and radius of a circle. This is going to be the same thing. We just happen to have a Z. So I'm starting by getting these in order. By order, I mean x next to x squared. I don't have a y term. If this 10 wasn't already on that side, I would subtract it, move it over, add it, move it over, whatever I had to do. Completing the square. Half of 2, 1, 1 squared, 1, circling it so I don't forget. Y squared, already a perfect square. Half of 10, 5 squared, 25, circling it. Why am I circling it? So that I don't forget that I also have to add it to the other side to balance the equation. X minus 1 squared, same sign, half of that. Y squared, looking good. Same sign, half of that, squared, equals, on this side I'm looking at a 36. The center of the sphere is going to be 1, 0, -5. The radius is going to be 6 square root of 36. I'll write that. I'm only doing one of those. Okay, vectors in 3 space. Guess what? This is easy. Here's why. Subtracting vectors. If you can subtract vectors that are x, y, you can subtract vectors that are x, y, z. This minus this, this minus this, this minus this. I pointed wrong, but you get it. Subtract the